Introduction. Where do we apply the concept of matrices? Matrices is used to obtain compact and simple methods of solving system of linear equations. Can we use matrices for various computer applications? Matrix notation and operations are used in electronic spreadsheet programs for personal computer, which in turn is used in different areas of business and science like budgeting, sales projection, cost estimation, analyzing the result of an experiment, etc.
Can matrices be multiplied?
Yes, we can multiply matrices. It has got a different method. Are you interested to learn?
Yes, teacher.
Okay. Today, I will teach you about the multiplication of matrices. Objectives. At the end of this lesson, you will be able to multiply a matrix by a scalar, explain properties of matrix addition, learn properties of scalar multiplication, learn the method of multiplication of matrices, explain the properties of matrix multiplication. Multiplication of a matrix by a scalar. There are two types of multiplication for matrices: scalar multiplication and matrix multiplication. Scalar multiplication is easy. We just take a regular number called a scalar and multiply it on every entry in the matrix. For the given matrix A, find 2A. To do the first scalar multiplication to find 2A, we just multiply a 2 on every entry in the matrix. 2A is equal to 2 into matrix row wise, first row 1, 2, second row 3, 4 is equal to matrix row wise, first row 2 into 1, 2 into 2, second row 2 into 3, 2 into 4 is equal to matrix row wise, first row 2, 4, second row 6, 8. So the answer is 2A is equal to matrix row wise, first row 2, 4, second row 6, 8. Negative of a matrix. The negative of a matrix is denoted by minus A. We define minus A is equal to minus 1 into A. Properties of matrix addition. The basic properties of addition for real numbers also hold true for matrices. Let A, B and C be m by n matrices, then A plus B is equal to B plus A, which is commutative property. Associative property, A plus B plus C is equal to A plus B plus C. Additive identity. There is a unique m by n matrix O such that A plus O is equal to A. Addition inverse. For any m by n matrix A, there is an m by n matrix B called minus A such that A plus B is equal to 0. Properties of scalar multiplication. All the laws of ordinary algebra hold for the addition and subtraction of matrices and their multiplication by scalars. The first property is, if A and B be two matrices of the same order and if K be a scalar, then K into A plus B is equal to K into A plus K into B. Another property is, if K1 and K2 are two scalars and if A is a matrix, then K1 plus K2 into A is equal to K1 into A plus K2 into A and K1 into K2A is equal to K2 into K1A. Multiplication of matrices. We can multiply two matrices if and only if the number of columns in the first matrix equals the number of rows in the second matrix. Otherwise, the product of two matrices is undefined. The order of the product of matrices is rows of first matrix upon columns of the second matrix. Method of matrix multiplication. Let's now learn the method to multiply two matrices. Let's take a general 2 by 3 matrix multiplied by a 3 by 2 matrix. The answer will be a 2 by 2 matrix. We multiply and add the elements step by step. We work across the first row of the first matrix, multiplying down the first column of the second matrix element by element. We add the resulting products. Our answer goes in position A, 1, 1, that is top left of the answer matrix. We do a similar process for the first row of the first matrix and the second column of the second matrix. The result is placed in position A, 1, 2. Now for the second row of the first matrix and the first column of the second matrix, the result is placed in position A, 2, 1. Finally, we do the second row of the first matrix and the second column of the second matrix. The result is placed in the position A, 2, 2. So, the result of multiplying our two matrices is the multiplication of matrix row-wise first row A, B, C, second row D, E, F, and matrix row-wise first row U, V, second row W, X, third row Y, Z produces matrix row-wise first row AU plus BW plus CY, AV plus BX plus CZ, second row DU plus EW plus FY, DV plus EX plus FZ. Example. Given the two matrices, determine which matrix product AB or BA is defined and evaluate it. Since A is 2 by 3 and B is 3 by 4, the product AB in that order is defined and the size of the product matrix AB will be 2 by 4. The product BA is not defined since the first factor B has 4 columns but the second factor A has only 2 rows. The number of columns of the first matrix must match the number of rows of the second matrix in order for their product to be defined. Solution. Taking the dot product of row 1 in A and column 1 in B gives the 1, 1 entry in AB. The 1, 1 entry in AB is 1. The dot product of row 1 in A and column 2 in B gives 1, 2 entry in AB. And the dot product of row 1 in A and column 3 in B gives 1, 3 entry in AB. The first row of the product is completed by taking the dot product of row 1 in A and column 4 in B, which gives the 1, 4 entry in AB. Now for the second row of AB, the dot product of row 2 in A and column 1 in B gives 2, 1 entry in AB. And the dot product of row 2 in A and column 2 in B gives 2, 2 entry in AB. Finally, taking the dot product of row 2 in A with columns 3 and 4 in B gives respectively 2, 3 and 2, 4 entries in AB. Therefore, AB can be solved to matrix row-wise first row 1, 3, -2, -2, second row -10, 11, -10, 19. Some points to be considered during matrix multiplication. If AB is defined, then BA need not be defined. Non-commutativity of multiplication of matrices. Even if AB and BA are both defined, it is not necessary that AB is equal to BA. Properties of multiplication of matrices. Matrix multiplication is associative. For example, given three matrices A, B and C, the following identity is always true. AB into C is equal to A into BC. Matrix multiplication is distributive across addition. A into B plus C is equal to A into B plus A into C. The existence of multiplicative identity. For every square matrix A, there exists an identity matrix of same order such that IA is equal to AI is equal to A. Example. Find x and y if x plus y is equal to matrix row-wise first row 7 0, second row 2 5 and x minus y is equal to matrix row-wise first row 3 0, second row 0 3. Solution. Given x plus y is equal to x minus y, mark it as 1 and 2. Now add the equations 1 and 2, we get 2x is equal to matrix row-wise first row 10 0, second row 2 8. Therefore, x is equal to matrix row-wise first row 5 0, second row 1 4. Now substituting the value of x in x plus y and solving it, we get matrix y is equal to row-wise first row 2 0, second row 1 1. Did you know? Matrices are commonly used in algebra to solve long equations. The variables such as x and y are taken away and the resulting numbers are organized into rows and columns to form a square or rectangular grid of numbers. These numbers are then calculated to more easily solve the problem. Summary. Let us summarize what we have learnt. Minus A is equal to minus 1 into A. A minus B is equal to A plus minus 1 into B. A plus B is equal to B plus A. A plus B plus C is equal to A plus B plus C, where A, B and C are of the same order. K into A plus K into B, where A and B are of the same order. K is constant. K plus I into A is equal to K into A plus I into A, where K and I are constant. We can multiply two matrices if and only if the number of columns in the first matrix equals the number of rows in the second matrix. A into BC is equal to AB into C. A into B plus C is equal to A into B plus A into C. A plus B into C is equal to A into C plus B into C.